the oceans absorb nearly half of the world's excess carbon emissions. This is how. Phytoplankton, microscopic plants. A cup of seawater holds nearly 250 million of them. Phytoplankton thrive on ocean nutrients, and like all plants, absorb carbon dioxide to live. Geoengineer Brian von Hertzen believes the oceans could capture even more CO2 if there were more plankton in the water to do the job.
These oceans are vast, they're huge, and they're so much bigger than the forests of the Earth that they really have the potential to make a big difference on the carbon dioxide problem.
When ocean nutrients are abundant, plankton populations can explode into blooms so vast they're visible from space.
These plankton have been recycling carbon dioxide for 3 billion years. They are recycling that carbon dioxide, which gets sunk to the bottom of the ocean.
To metabolize ocean nutrients, plankton must take in carbon dioxide. When they die, masses of them sink all the way down to the deep seabed, carrying trapped carbon from our atmosphere along with them. Brian von Hertzen is developing a geoengineering strategy to send even more of this carbon to the bottom. Brian wants to find a part of the ocean where plankton populations are lowest. It's these barren areas that offer scientists some of the best opportunities to stimulate new plankton growth.
Seawater density, the blue area is the warm.
There's hardly anything out here. I mean, it's like an aquatic desert.
Exactly. That's why there's so few coming up on the screen.
Plankton thrive when nutrient-rich waters from the deep ocean circulate up to the surface. But in this part of the North Pacific, normal patterns of water circulation prevent nutrient layers from mixing with surface waters. And that keeps plankton populations down.
You can see on this screen here, there's very few plankton coming in.
Von Hertzen's plan is radical and controversial. He believes if a way were found to bring nutrient-rich waters up from the deep to fertilize the ocean's surface, vast blooms of plankton would form. These blooms would absorb more excess CO2 from the atmosphere to strike a blow against global warming.
Being able to absolutely eliminate those carbon dioxide emissions would be an incredible goal to achieve.
To move the theory forward, Brian's made contact with two of the world's foremost oceanographers. Dave Carl and Ricardo Letelier have devoted their careers to studying how oceans and plankton work. Carl and Letelier believe the key to making plankton grow is to move nutrient-rich waters up from the deep ocean to the surface.
This water is fertilizer. This is the nutrient that will make the ocean green if we could only find a way to get it up there.
So if we can deliver this water up to the surface, we could effectively make a food delivery service for the plankton.
Their idea is to lift the deeper nutrient-rich seawater up to the surface artificially with seagoing pumps. The pump rig begins with high-strength ocean-going buoys. Hanging off them are tubes made of high-strength plastic. 1,000 feet long, they reach all the way down into nutrient-rich layers of water. As the buoys rise on the waves above, a column of deep water is pulled up the tubes to the surface to provide a steady diet of ocean fertilizer to turbocharge plankton growth. The pumps could boost ocean life in barren regions, but ultimately, there's an even bigger goal. Vast numbers of ocean pumps could raise levels of plankton so high, they'll create immense blooms. These super blooms could capture enough carbon dioxide to take a real bite out of global warming. And when the plankton die, a hefty percentage of them will take the carbon dioxide to the bottom of the ocean.
I'm very optimistic about this. We make a large array of these pumps, deploy them in the deep ocean, and we've actually wiped out America's carbon dioxide emissions, which is incredible.
Brian believes this system could deep six 1 billion tons of carbon emissions from the atmosphere each year. The oceanographers will test prototypes of ocean pumps at sea. They hope the results will advance a greater long-term goal: to help fight global warming by bringing the ocean's deserts to life. It's time to move on to the next challenge: construction of the ocean pumps. They're being built far from the waters of the North Pacific, on very dry land. The construction site is located on the outskirts of Albuquerque, New Mexico.
So this is a 30-inch diameter prototype, and this simply uses wave energy to open and close the flap right there.
The entire rig hangs from a surface buoy. A steel cable attached to the buoy passes down through the polyethylene tube to a one-way valve at the base. When the buoy falls off a wave, the intake valve descends, the flaps open, and deep ocean water floods into the tube. When the next wave lifts the buoy, the valve closes, trapping deep water in the tube and lifting it to the surface. Each time a wave lifts the buoy, the process repeats. A nearby soccer field is the only spot big enough to lay them out for inspection.
This is a big day. It's a big day for my lab, my team, the university, and especially for, we hope, for science.
We have a lot on the line in terms of getting these pumps into the water. No one has ever tried to pump using wave energy water from 1,000 feet deep up to the surface. So this is really a new development in that sense.
If Brian can prove his theory, huge pumps could be manufactured and deployed throughout the oceans of the world. Around the site, divers report a startling amount of sea life. It seems like a different ocean from the one they left behind 2 weeks ago.
We've got birds out there, we've got fish. It's really exciting because it's a good sign that there's a lot of productivity here.
Have the pumps succeeded? Has all this sea life been drawn here by a man-made plankton bloom? Out of the blue, a young whale shark. Adults are the largest fish in the oceans, and they feed exclusively on the smallest creatures, plankton. Whale sharks, plankton, ocean pumps. It's hard not to jump to conclusions.
For me, that whale shark is a compelling symbol. Here's the largest fish in the ocean, and it's there for a specific reason. It's there to eat plankton.
And what is our temperature difference? It's about 2 degrees.
Yeah.
Data shows the temperature falling as deep cold water reached the surface. The data peaks line up with the pulses from the pump strokes. No question, Pump 2 worked as expected.
This is the first step in a very long path to using this technology. The ocean pumps work. They brought water up from the target depth of 350 meters. So overall, this was a great success.
Ultimately, geoengineer Brian von Hertzen hopes that once the data are confirmed, pumps will be deployed throughout the oceans.
Once we prove this project and we demonstrate the ability to recycle carbon dioxide, we can scale this much larger. We can go to millions of pumps, and with millions of pumps, we can recycle billions of tons of carbon dioxide.
If you scale this up 1,000-fold or 1,000,000-fold and start putting these pumps everywhere you can, then we have to worry about the damage to the ecosystem. So these are real concerns that we need to look into, but it's no reason to stop the research. We need to move forward, but move forward with caution.
And we're going to be able to get these pumps to be reliable and be able to stay out here for months and years at a time.
If we ignore the ocean and keep pumping CO2 into the atmosphere, you know, this won't be good. The clock is ticking.
Most experts agree. The proverbial clock of global warming began ticking with the Industrial Revolution. Since then, we've pumped hundreds of millions of tons of excess carbon dioxide into our atmosphere. If we can't find a way to cut back our emissions in time, geoengineering our oceans might stop the clock, or even turn it back.